Good morning, everyone. Glad to be back again. Today we will be discussing multi-threading and multi-cores. I hope Professor Madhu was discussing the superscalar architecture, which is a follow-up to out-of-order issue, and he might have covered some half of it. He's going to cover the remaining part, but let's assume that you have a good high-level overview of what the superscalar architecture is, because some aspects of that is going to be needed when we talk about multi-threading. Okay, so today's lecture is going to have three parts essentially. After the introduction, we will discuss about multi-threaded architectures. Then we will talk about multi-cores, and then within multi-cores, we will specifically talk about the cache coherence related issue. Again, the cache coherence related issue will be discussing issues relating to caches, which will then lead to the discussions on memory consistency and consistency related issues, which again Professor Madhu Mutyam will cover sometime today. Okay, that's the sequence. We have gone a little bit out of order, but hopefully it should still be okay. So before we start talking about multi-threading, let's look at the different types of parallelisms that can be exploited in programs. We already saw instruction level parallelism as the basic parallelism that is supported in processors, and superscalar architectures support essentially exploiting instruction level parallelism. There are other architectures such as the very long instruction word architecture and the explicitly parallel instruction computing architectures, which also exploit instruction level parallelism. And this is still prevalent even in today's architectures. Apart from the instruction level parallelism, people also talk about what are called the thread level parallelism, in which multiple threads can execute in parallel. Each thread is essentially a sequence of instructions, and these different threads are either executed in what is called a multi-threaded processor or in a multi-core processor. We're going to see both of these things in today's discussion in this lecture, right? The other kind of parallelism that people talk about is task level parallelism, which is more like a coarse grain parallelism, where you talk about different processes and these processes interact with each other, right, by means of either a shared memory abstraction or by means of some kind of a communication abstraction, which is essentially what is called the task level parallelism. And again, task level parallelism is exploited in multi-core processors, or they could also be exploited in multi-processor systems, which essentially have multiple multi-core nodes, right, in them to exploit task level parallelism. The thread level parallelism is a fine grained parallelism where parallelism is exploited at a finer granularity, whereas task level parallelism, the parallelism is exploited at a coarser granularity. Then, of course, we can talk about the data level parallelism, which was originally exploited in the earlier days in vector processors and array processors. Subsequently, vector parallelism or data parallelism was exploited in the form of SIMD extension instructions. For example, if you look at your x86 processor architecture, they support what are called AVX instructions, advanced vector instructions, or the older day Intel processors used to support the multimedia extension instructions, MMX instructions. These are different forms of data level parallelism where multiple operations are being performed on different data items together. In today's context, actually, data level parallelism is exploited even more in the graphic processing units, where multiple threads execute together the same instructions on different data items. And this parallelism is also called SIMT parallelism, which is single instruction, multiple threads parallelism. But these are all different forms of data level parallelism, right? In this lecture, we are not going to focus on data level parallelism, but if you had a lecture on graphic processing units, or if you had lectures on advanced vector instructions and so on, they essentially exploit data level parallelism. Okay. Now, having talked about thread level parallelism, let's see how thread level parallelism can be exploited, right? As I mentioned earlier, each thread is nothing but an independent stream of instructions. So different threads essentially contribute to multiple independent streams of instructions. And these different threads are explicitly specified either by the application programmer that these are the different threads in the program, or they are extracted by a compiler, right? And typically, when these are extracted from the same program, they are extracted using some kind of basic thread libraries, something like pthreads, which is a basic way of expressing these threads and then exploiting parallelism across them. Or one could also use different kinds of libraries, such as the Silk library or the thread building block library, or programming languages, parallel programming languages like OpenMP, to expose the parallelism, thread level parallelism in the program. So essentially, what's happening here is that the programmer says that these are these different threads which can be executed in parallel. And this is how they synchronize, this is what they compute, and so on and so forth. And the underlying architecture, right, exploits this parallelism. One other thing about thread level parallelism is that it is not always the case that these threads have to be from the same process. You could also talk about threads from different processes. For example, in your desktop system, right, when you are browsing, right, your browser might be engaging multiple threads, right? You have multiple tabs, so there could be multiple threads, or there are multiple activities that are being done by the browser, which could be happening in parallel, right? These are possibly different applications even, right? For example, when you are running the underlying, when the operating system is running in your system, there is a background job that is running, there is a browser that is running, there is a music that is being played, etc., etc. So there could be different threads which are possibly from different applications which could be executing together on your system, and the processor, underlying processor, could be exploiting thread level parallelism among these things. So when we talk about thread level parallelism, we may be either talking about thread level parallelism from the same application or from different applications. In fact, the parallelism can also come from different users. For example, when you talk about services like let's say the Google services, right, where the request may come from different users which might be executed in parallel, and there is no dependency between these requests, and therefore there exists automatically some level of thread level parallelism, or there exists enough thread level parallelism among the requests which could be exploited. So there are different ways in which the thread level parallelism can manifest, and irrespective of what way it manifests, if the processor is able to exploit it, right, then we are going to get thread level parallelism. Okay, now what are the architectures to support thread level parallelism? We could think in terms of building what is called a multi-threaded architecture, which was originally proposed way back in the well, actually multi-threaded processors existed even from the late 60s onwards, but one could actually think of the first instance of a multi-threaded processor to be proposed in the mid-80s, what is called the Denelker heterogeneous element processor, which is a multi-threaded architecture. Okay, but we will talk about multi-threaded architecture even in the context of a simple superscalar pipeline, which can support multiple threads, right? So we will talk about that. And we will also talk about what are called multi-core processors, or what is also called as the chip multiprocessing, which can also be used to exploit thread level parallelism, where the different cores can actually execute the different threads. In the case of the first one, multi-threaded architecture, there is a single core, there is a single processor core, right? And many of the resources in that single processor core are actually shared by multiple threads. There are certain other resources which could be either replicated or which could be partitioned across the threads, right? And together, right, but there is only one set of resources which is underlying that. And that one set of resource, like pipelines and so on and so forth, right, is being shared by multiple threads to execute these threads in parallel. Let's see how that happens, right? So initially we will focus on multi-threaded processors, and then later on we will talk about multi-core processors. It's also possible to combine these two things, that is having multi-core processors where each core is also supporting multiple threads. In fact, if you look at your desktop processor like the Intel Skylake processor or the AMD processor that you have, right? They already have multiple cores. That's what you see as um, 4 physical cores, and they also support multi-threading, and that's why they say that 4 physical cores and 8 logical cores, right? Where the logical cores essentially come from supporting multiple threads at the same time. Okay, so let's focus on the first part first, right? That gets us to our discussions on multi-threading. Okay, so originally multi-threading was proposed to tolerate latency. So when we say tolerate latency, you can recall that in the case of operating systems, when there are multiple processes which are there in the system, the operating system used to do a context switch from one process to another process whenever a process is going through some form of an IO. And this is essentially to make sure that the processor resource is not simply idling when the other process is doing input output. And this is when it will do a context switch from that process and then move on to another process and then start executing that. The same idea can also be applied to different threads, and then you can do a context switch from one thread to another thread and start executing the thread when the first thread has encountered some long latency operation. This long latency operation could be, let's say, for example, an L2 cache miss, right? Or it could be a synchronization operation, or it is a dependency waiting for, let's say, a long latency floating point operation to complete, and so on and so forth. In the case of operating systems, you are talking about an IO time which could be in the order of several milliseconds of maybe even millions of cycles. Whereas in the case of multi-threading and then the switching between different threads, we are talking about latencies which are not really that large. Maybe it's about 100 cycles or a few hundred cycles, but you still want to do a context switch, or maybe it's even few tens of cycles, not even hundreds of cycles. Maybe it's just few tens of cycles, right? You want the processor to do a context switch or a thread switch from one thread to another thread and then start executing the other thread when the first thread is stalled for certain reasons. In order for this to be done, right, the thread switching overhead has to be very minimal. Because if you're doing a context switch, if you're doing a thread switch to save 10 cycles, right, you can't be spending a large number of these cycles just for doing the context switch saving and restoration, right? Context saving and context restoring. Okay, we will come to that aspect a little later on. Okay, the other reason why multi-threading was introduced is that as people started building these superscalar processors and more complex superscalar processors, they also found that the extent of instruction level parallelism which can be exploited by the superscalar processors is still limited. Right, this is limited because of various reasons. For example, the dependencies in the program or hardware resources like instruction fetch or memory bandwidth, instruction fetch bandwidth or memory fetch bandwidth, right, etc. are limited. And also we have constraints with regard to branch predictions. Even though you can have complex branch predictors, still you can't predict everything 100% accurately. And in deeper pipelines, even if you predict, there are certain other stall cycles which were involved in that. So as the complexity of superscalar processors starts increasing more and more, the returns from it in terms of the extent of instruction level parallelism. Is there a question there? Okay, so the extent of instruction level parallelism which is being exploited, right, or the gains that you get out of the instruction level parallelism started slowly saturating. And that's another reason why people thought that they have to move from just instruction level parallelism to other forms of parallelism. And that is where they thought about exploiting thread level parallelism. An interesting idea that came about in the mid 90s is that you could actually extract a higher instruction level parallelism from different threads. That is, pack independent instructions from different threads together in a single superscalar issue weight and exploit instruction level parallelism there. We will talk about such kind of a proposal in our discussion today. Okay, so that's essentially trying to make sure that the system resources are utilized well, and this is the primary reason why they have proposed multi-threading. Okay. Now, as I mentioned earlier, each thread is an independent stream of instruction, and each thread may have a set of states. This could be certain local variables for the thread, and they could also be using some number of processor registers, right? So when you want to do a context switch or a thread switch from one thread to another thread, you have to make sure how the states of this thread are maintained. For example, if a thread is using certain number of registers, right, and you want to do a thread switch, what happens to these registers and their values? Do you save and restore them, or what exactly is being done? What about the local variables of the thread? Where are they kept, right? Will they be retained when you do a context switch and then come back at a later point in time, right? Those are the issues and concerns that we need to address, right? So the old thread's context needs to be saved, and the new thread's context has to be restored on a thread switch. And this overhead of saving the context of the old thread and restoring the context of the new thread is essentially what we are going to call as the context switch overhead. And when you do thread switching to avoid latencies which are very small, like say in the order of few tens of cycles, then your context switch overhead or your thread switch overhead time has to be minimal. Okay, so in order to achieve this minimal thread switch overhead, what we are going to do is that certain states of the thread which which needs to be retained, instead of saving and restoring, we are going to dedicate resources for holding on to that, right? For example, when you talk about registers, each thread may have, let's say, 8 registers which it might be using. Then if I have, let's say, 4 contexts or 4 threads which are concurrently running in my processor, then I will allocate 8 threads for each one of these 8 registers for each one of these threads, and would allow them to hold on to that registers even when they do a context switch, right? That means that during a context switch, they will have their values in the registers, and no other thread can actually use that register. I just gave 8 as an example, but for example, if your architecture supports 32 registers, then you can say that the register file is replicated so that each thread will see the entire register file for itself. That means that you will have, let's say, if there are 32 registers in the register file, and if there are 4 contexts or 4 threads, then you will actually have 4 register files, each of size 32, so that every thread can actually hold on to its state as far as the registers are concerned, even when they have been switched out of the execution. This is for certain states. For certain other states, we might be doing something else. For example, what happens to the caches, right? To allocate one separate L1 cache for each thread may be too large, right? It may actually lead up to other hardware complexities, right? So in that case, what happens is that things like caches, right? For example, is actually shared across the different threads, right? So whichever threads, whatever value, they will actually bring it to the cache. And because if 2 cache blocks are brought to the same set, and I mean, depending on the associativity, you can only support certain number of blocks from which belong to that set. Beyond that, you have to replace some existing things. So you allow these things to actually share them, dynamically share the resources. That's how a caches are being shared. Now, if you look at other things, so let's see. This diagram really explains what this is. So you could see a superscalar architecture over here, which has the program counter, and the instruction fetch is being done by accessing the instruction cache. The fetched instruction is being put into the set of instruction registers or instruction buffer, and then when it goes for execution, right, it is going to access a register file. Now, because you have multiple threads, you essentially have multiple register files, right? Each thread having its own set of register files. Then the instruction execution is being performed. If it has to write into the cache or read from the cache, then it actually reads the value from the data cache, which is dynamically shared across all of these threads. Okay, there are also various other hardware structures in the processor. For example, yesterday we talked about the reorder buffer, right? The reorder buffer is also shared across the different threads. We talked about the branch prediction hardware, the branch prediction tables. They are also shared across the different hardware threads. But each thread will have its own set of general purpose registers and possibly its own set of program counter, right? And they may be replicated. So as you can see that in a multi-threaded processor, by replicating a few resources, in this particular case replicating the PCs and the register file, but then sharing the rest of the resources, you have now come up with an architecture which can support the execution of different threads, right? So each thread will have as its own program counter, and therefore that specifies, right, where is the next instruction that has to be fetched for execution in that particular thread. And when you do a context switch, you essentially say that instead of using PC1, I'm going to use PC2, or instead of using PC2, I'm going to use PC4. And PC4 is the one which is going to be used for instruction fetch, and you're going to fetch instructions from that, right? And the moment you say that you're going to fetch instructions from PC4, then that particular instruction has to read register files corresponding to thread 4, and so on, right? So by minimally replicating some of the resources, you make sure that your processor is now capable of executing multiple threads together. It's not that they are executing them together. Whenever one thread is stalled, the other thread is going to start executing its instructions. And when that thread stalls, you might want to switch to some other thread and start executing these instructions. This way, the stalls that are incurred in the pipeline now are being covered or being masked by instructions from the other thread. And that is how this ensures that your hardware resources or the utilization of your hardware resources is improved. And here the important resource that is considered is the functional unit. So you want to always keep the functional unit busy, the execution unit busy, so that it can keep executing instructions. In order for you to do that, when one thread is stalled and you could not supply instructions from the instruction queue to the functional unit, you take instructions from another thread and then start giving it as you have done a context switch, right? That's essentially the idea here. Okay, now let's spend the next 10 minutes or so trying to talk about how multi-threading is implemented, what are the issues, which resources are shared, how, and then how the different threads are being scheduled. Okay, so as we mentioned earlier, these resources in a pipeline are going to be shared, and let's see how this sharing happens. When you talk about resources which do not have any associated state with them, for example, let's say the functional units or the arithmetic and logic units, right? They are simply shared across all the threads, and they are essentially time multiplexed. That means that in different cycles, possibly instructions from different threads may be executing on them. Okay. Whereas when you talk about a persistent hard state like the program counter and registers, and as I mentioned in the previous slide, they are replicated. Each thread has its own set of register file, and program counters and so on. Certain other persistent states, which are soft persistent states like caches and branch predictors, right? They are partitioned and they are dynamically partitioned. As and when the access is made to certain regions in the cache or certain regions in the branch predictor, those regions belong to a particular thread, or that particular thread makes use of those regions. So, for example, depending on the program counter value, a branch predictor would access the branch prediction buffer or the branch target buffer location. Then that particular location, depending on the PC value, would then correspond to the given context, right, or the given thread. And when you talk about microarchitectural structures such as the reorder buffer or the reservation stations or the load store queue and so on, they are transient states. They are also shared between different threads, and the way in which the sharing happens might depend on how exactly the different threads are being scheduled. Okay, We will first see how the different threads are being scheduled, and in that context, I will make a comment about how this sharing is going to happen. And this sharing might happen either as a statically partition, like you statically partition the reorder buffer into multiple chunks and give each chunk to one of the threads, or you can do dynamic partitioning of these resources. It depends on how the multi-threaded architecture is implemented and how scheduling between different threads happen. Okay, so talking about scheduling between different threads, the important question that we need to ask is that when do we switch from one thread to another, right? And this depends on what latency you want to hide. If you want to hide, let us say, an L2 memory latency or an L2 miss latency, then on every L2 miss, you could switch from one thread to another thread. But let's say if you have a deeper pipeline and you want to actually hide the deeper pipeline's latency, then you might want to switch on every instruction execution because you don't want to have these longer dependencies being seen by the individual instructions. Okay, I'll give you an example of that as we go by. Right. So, depending on this, there are three different forms of multi-threading that have been proposed. What is called the coarse grain multi-threading approach, or what is called the fine grain multi-threading approach. The third approach is what is known as the simultaneous multi-threading, where, as I mentioned earlier, right, the architecture tries to pick operations from different threads and pack them together and give it for the superscalar processor for executing. Right, that is what is called the simultaneous multi-thread. Okay, so in the case of a coarse grain multi-threading, is there a question there? Okay, in the case of a coarse grain multi-threading, right, when a thread is stalled on some event, right, a thread switch happens. For example, the stalling event could be an L2 cache miss or an L3 cache miss, or it could be a synchronization event, right, or it could be a long latency floating point operation such as a floating point multiply or divide, and you don't want the latencies of the floating point multiply and divide to be stalling the pipeline for a long time. So you may want to switch to a different thread and start executing instructions from that. So let's look at how coarse grain multi-threading works. So if you consider the superscalar processor, let's say at each cycle you start executing some number of instructions, whatever instructions that are independent, which can be executed in parallel depending on the instruction level parallelism you have, you will execute those instructions, right? So for example, in the first cycle you executed 3 instructions, in the next cycle you executed 2, and so on and so forth, right? Now at this point in time, let's say this one of these long latency operation, right, has come and the pipeline is stalled, right? So when the pipeline is stalled, you could either wait for the long latency operation to complete and after that start resuming instructions from the same thread and execute them, in which case you would have wasted 4 cycles. In fact, if you look at it from the superscalar point of view, right, because you could execute 4 instructions in each cycle, if you have waited for 4 cycles, you have essentially wasted 16 slots of instruction execution, right? Instead, if you have done a context switch and if you have switched from one context to another context, right, or one thread to another thread, and if you have started executing instructions from there, and again after executing a few instructions, let's say another long latency, right, event has happened in the second thread, then you could possibly context switch back to the first thread if it is ready by that time, right? By doing this, what we have done is that we have slaved, right, some of the slots which are wasted otherwise. Okay, the cycles that you see in between here are what are used for doing the context switch, that is saving the context of the old thread and restoring the context of the new thread. In the fine grain multi-threading, what happens is that when you do a context switch, you essentially allow the pipeline to flush, right? And because you allow the pipeline to flush, you also want your pipeline to be not very deep. Okay, it's a shallow pipeline. It has only few stages in it, so that you can allow the pipeline to drain and you can make sure that when the next thread executes, it has the pipeline entirely for itself. This is not mandatory for all multi-threaded architectures. For example, when you when you support fine-grained multi-threading, you could actually share the pipeline, and then different instructions from different threads can actually coexist in the pipeline. It so happened that in the case of a coarse-grained multi-threading, they wanted to make sure that the pipelines are completely flushed before you move on to the other thread. Okay, now let's look at, so one example of this coarse-grained multi-threaded architecture is the IBM North Star architecture. Okay, but let's now look at a fine-grained multi-threading. In fine-grained multi-threading, you do a thread switch, right, between different threads on every cycle. That means that irrespective of whether a long latency operation has happened or not, right, the processor would switch from one thread to another thread in every cycle. Therefore, if you look at your superscalar processor, then what happens is that in cycle 0, you would have executed instructions from the first thread. In cycle 1, you would execute instructions from the second thread. In cycle 2, you will execute instructions from the third thread, and so on, right? And by the time you come back to cycle 1, you would have actually spent some number of cycles. For example, let us say if the processor pipeline is, let's say, 20 stages deep, and you don't want these latencies between operations to affect and then create a large number of stalls. And if you can actually have up to, let's say, 20 different thread contexts possible to be held in the process simultaneously, and if you do a context switch on every cycle, then what happens is that at the end of the 20th cycle, again, you will go back to thread 1. And by that time, it is guaranteed that the first thread, right, its ith instruction would have completed its execution. Therefore, you can start the I+1th instruction, and therefore, any data dependency that it may have would have already been satisfied. So, fine-grained multi-threading is essentially used to address issues relating to deep pipelines, right, and to address or resolve these dependencies of deep pipelines. Okay, but in order for you to do this and then switch context from one thread to another thread, your context switch overhead has to be really 0 cycles, because if you incur even one cycle for every context switch, then that's a wasted context, right? That's a wasted time, right? So typically in fine-grained multi-threading, each thread would have its context always available with it. There is no saving and restoring of context. It is just that you go from one thread to another thread on every cycle, and the context switch overhead time is 0. That is why it is possible to switch between different threads on every cycle. Okay, but obviously this requires more number of threads, at least as many threads as the depth of the pipeline, and perhaps even more. Okay, and what happens here is because you are switching context on every cycle, each instruction is going to get processor resources only once every 20 cycles or once every n cycles. And because of this, right, the single thread performance is going to be affected. But the system throughput would still be improved. Okay, now let's talk about the third form of multi-threading, which is what is called as the simultaneous multi-threading. In simultaneous multi-threading, what happens is that instructions from different threads which are ready to be executed are packed together and sent in each cycle of instruction execution. So if you can think of your superscalar processor, then in cycle 0, let's say if there are 3 instructions which are independent and are ready to be issued from thread 1, and 1 instruction which is ready to be issued from thread 2, then you pack all of them together and then issue it in the first cycle. Right? Similarly, in some other cycle, maybe there are 3 instructions from the third thread and then 1 instruction from the first thread, which you can pack together and then issue, and so on and so forth. Right? Every one of these colored cells represent instructions from one different thread, and the white cells are the wasted stalls. So as you can see, compared to the previous diagram, in the case of simultaneous multi-threading, right, you have fewer stalls which are being incurred. And this is what I meant by saying that you take instructions from different threads. That is, you take thread level parallelism and then you convert it into instruction level parallelism by executing them together in the superscalar processor. Okay, this simultaneous multi-threading is essentially what is also known as hyper-threading, or as a variant of this is what is known as hyper-threading in your Intel and AMD processors. Okay. There are some issues or complications with regard to sharing of the register files and ROBs and things like that, but we will not get into those details here. Okay. Now, just to summarize things, so what we have seen so far, in the case of a superscalar processor, whenever there is a long latency instruction that stalls the processor cycles are wasted. Whereas in the case of a coarse grain multi-threading, you could do a context switch and then you could start executing instructions from a different thread. In the case of a fine grained multi-threading, you actually do context switch on every instruction and start executing instructions from different threads. But within each cycle, you only have instructions of the same thread. Lastly, we have the simultaneous multi-threading architecture in which you could actually pack instructions from different threads and issue them on the same cycle. Okay, so what are the design challenges or issues that multi-threading poses? Because there are multiple contexts that have to be supported and each context requiring its own register file, you will now require a much larger register file, physical register file to be provided. And because soft structures like ROB, load store queue, etc. are shared between these threads, it is beneficial to increase their size a little bit and then share them so that the interference between these different threads do not affect the performance significantly, because you do need to have some amount of ROB for each thread. So what you do is that if your original ROB may be, let's say, 128 entries, you probably increase it maybe to 192 entries or 256 entries if you want to support 4 threads and so on. One thing that you can't avoid is that there is certain amount of interference between the threads which are executing concurrently. Because there are 4 threads which are executing concurrently in a multi-threaded processors, they are going to be sharing the same resource like your caches and branch prediction hardware and so on. And because of this, there could be interference. One thread might be bringing in some data which might remove the data which was brought by another thread. It might be evicting data which was brought by another thread. This kind of an interference is something which is unavoidable, but it always comes with the multi-threaded architectures. To reduce the impact of this, again, one could increase the size of the cache by a small amount. Right? The same thing also holds for structures such as the translation look-aside buffer. Okay, again, to conclude, multi-threading has advantages in terms of tolerating latencies. It can increase the utilization of the pipeline by avoiding the stalls. It can also improve the extent of instruction level parallelism by packing instructions from different threads. Okay, but the downside of multi-threading is that it actually reduces the single thread performance. Single thread performance goes for a toss, right? And then in architecture such as the coarse grain multi-threading, when you do a context switch, it can also introduce problems relating to fairness. Okay, so modern day processors, if you talk about them, all your processors like your Intel and AMD processors, they support hyper-threading. Processors such as the IBM Power 9 processor can support up to 4 threads in parallel. The Sun Niagara processor can also support more number of threads and so on and so forth. More importantly, when you talk in the context of the graphic processing units, the graphic processing units essentially supports multiple threads, and it does multi-threading of a group of threads called warp, right? And then in a GPU, particularly in a streaming multiprocessor in a GPU, right? You do a context switch from one warp to another warp, right? And again, the idea is very similar to multi-threading. In fact, that is the idea is multi-threading there. And then when instructions from one warp suffer some kind of a long latency operation, the warp scheduler can switch from one warp to another warp in the GPU and start executing instructions from another warp, which is nothing but a group of threads. Okay, so that essentially summarizes the multi-threaded architectures and where multi-threaded architectures are in today's context. If there are some questions, I can quickly take them before I move on to the next part, which is on multi-cores. Are there any questions?
I have one question. I'm sorry if it's a little bit irrelevant. So, with respect to hyperthreading, one common marketing speak I've seen that they refer to like an 8-core 16-thread processor as having 16 virtual CPUs. Like,
Right.
yeah, so given that like multi-threading still has some restrictions on how resources are shared, is it accurate to say that like a processor with 2 threads per core actually has like can it be actually called a
You
virtual
you you
CPU, or
already
is that
you already answered the question, right? You said it is a marketing.
yeah? So this is not actually accurate, right?
Correct.
Yeah,
Correct, right?
thank you.
So when you actually try to, you can actually experiment these things, right? For example, when you write multiple threads and then try to execute it on your multi-core processor, you can see that as long as you have one thread per processor, you have, let's say you experience a performance of X, then you put 2 threads per core and then you see what is your performance, right? It won't be 2x. It may be 1.2x or 1.1x. Even Intel or AMD in their websites, when they talk about the processor's performance, right, there are many metrics that are given there. If you look at it by exploiting multi-threading or by exploiting hyper-threading, you're going to improve your processor performance by 10 to 15%, roughly speaking, right?
Yeah,
But as you correctly pointed out, it's a marketing trick. They just call it as 2x number of logical
yeah,
cores.
yeah,
Yeah.
yeah. Thank you.
Yeah, it's a very relevant question.
Sir,
Yeah.
I've also seen in some let's say performance engineering or let's say benchmark evaluation, sometimes people let's say people prefer to disable hyperthreading while evaluating a benchmark.
Correct.
So can you let's say describe
So
some reason?
you remember the thing that I mentioned about single thread performance,
Yes, a single thread performance. Yes.
right? So if you want to get single thread performance, you have to disable multi-threading,
Okay.
right?
Okay.
Particularly if the different threads are from different applications, then the single application's performance is lost, right? So when you enable multi-threading, and if you don't have control in terms of which thread is actually scheduled along with, let's say, your user application, right? Say for example, let's say you are running an important application and you are trying to do a performance measurement, and if some other application or thread from some other application is coexisting with your thing and executing, then you lose performance. The other thread also gets some performance. Overall system performance improves, but your thread's application performance goes down, right? That's the reason.
Okay.
Yeah.
So in this context, can you elaborate on kernel level threads and user level threads?
Okay. So maybe I should defer that question. Let's do one thing. Let's come back at the break time and then see what we want to answer in that question, because this is well, actually, yeah, maybe we'll do that at that point in time.
Right.
Okay, it's somewhat orthogonal to this, so we will take it at that point in time.
Understood.
Okay, let's move on. Okay, the next thing that we want to talk about is multi-cores. As you can see, in multi-threading, there is some amount of hardware replications or some additional hardware that has been put to support multi-threading. Whereas in the case of multi-cores, right, each core is going to be replicated. then you might want to ask what really drove this multi-core situation. So let's just go and look at what has happened there, right? And why this evolution, or why multi-cores were actually proposed, and why this will become successful. Okay, let's just look at it. So let's just quickly recall Moore's law. Moore's law essentially says that the number of transistors in a chip doubles every 18 months to 2 years. And associated with this doubling of chips, we have also seen an increase in the performance, right? Um, and one could also see that with this increase in the number of transistors, right, computer architects have actually come up with intelligent techniques which can improve the performance of the processors by doing things like pipelining or instruction level parallelism and so on. And one associated trend that was also happening with this increasing number of transistors is that the transistors were becoming faster. That means the clock rate with which we are operating was also increasing. And this was happening because of what is called as the Dennard scaling. Dennard scaling is essentially observing that as the feature size of transistors decreases, you have more and more transistors, but their voltage and current reduce proportionately. And they also can operate on faster clock frequency. And because you can operate them on faster clock frequency with reduced voltage and current, their power budget essentially stays at the same thing. So if you look at it, what was happening is that as there is scaling in the feature size, as the feature size was reducing, the number of transistors were increasing, which is what is due to which is what was observed in Moore's law. And at the same time, the voltage is reducing, the transistors are becoming faster, or the clock frequency is increasing, and the power budget, on the other hand, is remaining constant. That means that you are able to pack twice as many transistors in the same chip in 18 months and at the same power budget. And this was very nice because this is what what was happening in the microprocessor industry in the 90s and early 2000s. Right, they were having more and more transistors, bigger caches, various things were happening, and the process clock rate was also increasing. Because of all of these things, right? So this is the trend which shows that the processor clock rate was steadily increasing, right? As you can see that in the x-axis, you could see the year, and y-axis you could see the clock frequency, and you could see that processor clock frequency increasing all the way up to some 3.2 gigahertz, and then somewhere there it was saturating. We'll come to the saturating part in the next slide. Okay, so the combination of Moore's law and Dennard's law essentially stated that you are going to have more and more number of transistors at the same power budget and faster clock frequency. This essentially meant that the processor's performance are actually doubling, and that was actually a very nice thing, and programmers need not have to worry about anything. Their single-threaded application were actually scaling very well or performing very well, and their performance was increasing with future generation processors, right? But then in the early 2000s, people started these clock frequencies to be saturating. The reason for that is because of the increase in power. And why was this power increasing? It is because the Dennard scaling has stopped working, right? And this has happened because of the following reasons. Power essentially consists of two components, what is called as the dynamic power and the leakage power, right? As the feature sizes were decreasing, the dynamic power is what is really decreasing, whereas the leakage power stayed more or less constant. So as the scaling was happening, right, at some point in time, the leakage power started dominating the overall power. And therefore, with reductions in feature size, since the leakage current remained the same, right, Dennard scaling no longer holds good. And because of that, and also as you go, as you increase the feature size, or sorry, I should put it the other way around, as you decrease the feature size going from, let's say, 0.14 nanos, this thing, to 0.14 nanometer to let's say 0.7 nanometer or 0.1 nanometer, the challenges in scaling were much higher. So Moore's law was slowing down. It has not stopped working, but it has slowed down. Whereas Denner's scaling has stopped working. Because of these two reasons, you are actually seeing that even in the same transistor, you are going to have more number of transistors, but the power budget is going to increase, or you can't at least increase the clock frequency anymore, right? So this has resulted in saturating the clock frequency, right? And but on the other hand, you have more number of transistors. What do you do with these transistors, right? You could build, let's say, a wider width superscalar processors. You could build a much more complex branch prediction hardware, or you could build a few other things, but then they may not necessarily give you better instruction level parallelism, because we already saw the instruction level parallelism in applications is limited. So what people started doing is that with this increased hardware, or with this increased number of transistors, they started putting more and more processor cores in the chip. So this is what that drove the multi-core era, right? So in the early 2000, instead of increasing the processor clock frequency, people have started building multi-core processors. So first in the early 2000, the IBM Power 4 processor was released with 2 cores in a single processor. As you can see here, there are 2 rectangles, red rectangles, right? Each one corresponds to 1 core. That's having the instruction fetch, right? The execution unit, floating point execution unit, load store unit, and so on and so forth. There are 2 cores, and of course, there is some amount of shared L2 cache in the architecture. Soon enough, Intel also came up with 2-core and 4-core architectures, and here is a dice shot of an 8-core architecture, where you could see that there are 8 independent processor cores, which means that the entire processor data path, instruction fetch, decode, register renaming, your reservation stations, instruction queues, your pipelines, everything is replicated, right? So each core has an entire processor data path. So like that, you have multiple cores, right? And in addition to these multiple cores, you also have some, okay, so before I go to that, within each core, you also have its own L1 cache, L1 instruction cache, L1 data cache, and so on. And some architectures even supported a private L2 cache as well within each core. In addition, you also have what is called a shared L3 cache, which is shared across all the processor cores. And of course, you also have other peripherals, right, and some queues and interconnect networks, which is connecting all of these different cores, and also a memory controller, which is meant for communicating with the DRAM devices, and so on. Okay, so if you look at a multi-core architecture essentially consists of multiple processor cores, which is what is called the core part of the multi-core architecture, and it also has what is called an uncore part, which is nothing but the shared L3 cache, the queue, the IOs, and the interconnect network into it, right? So that's exactly what it is. Multiple cores, each core having its own processor pipeline, register file, L1, L2 caches, and then the uncore part, which is basically the shared L3 cache among the cores, the memory controllers, the interconnect, plus possibly optionally other accelerators, and so on and so forth. Okay, now let's look at what is the interconnect, how the different processor cores are connected across each of them, right? So one simple interconnect network that you can think of in connecting these different cores and the shared L3 cache could be by means of a simple bus, right? So for example, in this case, I have 4 cores, each core having its own private cache, but there is a shared last level cache which is shared across all of these cores, and they are connected to the shared cache by means of a simple bus, right? And of course, if the data is not there in the shared last level cache, the request is sent to the memory controller, which in turn interfaces with the memory or DRAM and gets the data. Okay, so the interconnect network in this particular case is a shared bus. In a shared bus, at any given point in time, only one core can use the bus, right? Because only one request can be put on the bus. If there are multiple cores which want to access the shared interconnect network, then some arbitration has to be done between them, right? There is an arbitrator which is going to decide and then tell which core would use the bus at a given point in time. But the advantage of the shared bus architecture is that other cores can actually snoop on the bus. That means that they can listen to what is going on in the bus. But if two cores try to communicate at the same time, that's not possible because you have to arbitrate between them. That will corrupt the bus. So you have to arbitrate between them. However, when one core is communicating on the bus, the other cores can snoop to that or listen to that. Okay, this is an advantage, and we'll talk about this when we talk about the cache coherence protocols. Okay, the bus is also the simplest interconnect network that you can build, and the bus does not scale when you have a large number of cores. For example, if you have more than 8 cores, the bus interconnect network no longer scales. So one goes for certain kinds of point-to-point kind of an interconnect network, and in this point-to-point interconnect network, right, essentially there is a packet switching that happens. There are many switches, and the packet goes from the source to the destination by going through these different switches. And this is pretty similar to what you have seen in your networking course. And in many of these interconnect topologies of point-to-point interconnect network, depending on the structure, it could actually support multiple messages which are in flight. Okay, so one possible interconnect topology is the crossbar interconnect topology, where each core, right, is connected to one or more number of switches, or is connected to, in this particular case, one switch, which in turn is connected to other switches and so on. And the shared last level cache is actually divided in terms of multiple banks, and these banks are also connected to the crossbar network. So what you can see here is that in the case of a crossbar network, there are multiple switches. For example, if let's say if the core 1 wants to communicate to bank 2, then the connectivity is such that this switch is connected or enabled so that it can allow core 1 to connect directly to bank 2. And when core 1 is directly talking to bank 2, maybe core 2 can talk to bank 0, or core 3 can talk to bank 1, and core 4 can talk to bank 3, and so on. So parallel connections or multiple messages can happen in parallel as long as the source destination pairs are different. Okay, yet another interconnect network is a ring network, which is basically an extension of a bus interconnect network, except that now you have these point-to-point things which connect these cores and banks together in the form of a ring. So in this particular case, if core 0 wants to connect to bank 1, then it will send a message through these switches, and then after a few number of hops, it will reach the required bank. And again, because each one of these link is a point-to-point link, at every cycle, each link can carry a message, and therefore this also supports multiple in-flight messages. Okay. In the case of a mesh interconnect topology, we basically have a two-dimensional structure, right? You can just think of it as a two-dimensional grid, and the banks and cores are connected to this two-dimensional grid of switches so that they could communicate. So here you talk about what is called, if this bank wants to communicate with this, if this core wants to communicate with this bank, then the message will actually go through this path and then reach this. Or if this core wants to communicate to this particular bank, then the message can reach through this path and through these switches to that. So there are different kinds of interconnect networks that are possible. And these interconnect networks are used in different processors. For example, the ring is used in the Intel Sandy Bridge, the mesh is used in the Tyler T64 architectures, and so on and so forth. And the interconnect network essentially forms a significant part of the uncore part of the architecture. Okay, now are there any quick questions here before we move on to the next part, which is about shared memory and distributed memory architectures?
One more question. Basically, recently we've been seeing a lot of these microcode hacks, right? Like Spectre and Meltdown, where due to speculative execution, and even in Apple, there's a bug that allows two applications executing on the same processor to exchange data with each other. So, is this a weakness of the multi-core design, or is it like this because nobody is willing to trade speed for security? Like, is it inherently unsafe?
Well, let me just, okay, again, this would require a more detailed answer. I'm not sure whether we have time for that. But what was really happening is that if I look at Spectre or Meltdown, this is essentially a processor feature such as speculative execution, right? But
Yes.
what the exploits were doing is that when speculative execution was happening, you are actually fetching and executing instructions from the wrong path, and that information is what is exploited in all of these things. Okay, some careful redesign of that could actually stop that leak. Okay, so one could say it was an oversight that people did not expect these leaks to be exploited. That was really what was happening. Okay, so if you see, just look at your buffer overflow.
Yeah.
Right. I mean, it's not it was intended that way, or you were trying to get something because you want to expose that. It's not like that. But it wasn't intended that way, and people started exploiting. Then you said, okay, now if people are going to be exploiting this, then I should probably close these things, and then make that more secure. So this is always going to happen with security, right?
Yeah,
So
got it.
that's really what is the deal. Okay.
Yeah, thank you.
Sure.
Sir, I have one question. So, recently, what happens is, let's say, high performance processor comes with kind of let's say 2 socket 16 core. So 8 core is divided.
Could you just hold on to your question, because the next set of slides are exactly on.
Okay.
Okay. We'll come back and then ask you. I mean, give you time to ask this question. Okay. All right. So what we have seen so far is that we have seen what a single multi-core architecture could contain. But let's look at the parallel architectures and then try to understand those different types of parallel architectures and how, using multi-cores, we can implement those parallel architectures. One form of a parallel architecture is what is called the shared memory architecture, where you have multiple processors, right, each having its own private caches connected to memory by means of a network, interconnect network. So there are different processors or processor cores, if you want to think of it that way, connected through an interconnect network to a set of memory modules. Now, the interaction between the processors or the processes which are executing on these processors are by means of the shared memory, and any processor is able to access any locations in any of these memory modules, right? So that kind of an abstraction is provided in the shared memory architecture, and this particular architecture is essentially what is called as the centralized shared memory architecture, right? Because the memory is centralized to all the processors. This architecture is also called as the uniform memory architecture because the latency it takes for any processor to communicate with any memory module is same, because it has to go through the interconnect network. Okay. As opposed to this, in the case of a distributed shared memory architecture, right, we have a set of we have a processor with its own private cache and some part of the memory which is local to the processor. Like this, there are many such modules which are connected with each other. and all of these are connected by means of an interconnect network. Now, in this case, what's happening here is that if this processor wants to access certain memory locations, which is over here, then the latency of that is shorter because it doesn't have to go through the interconnect network. Whereas if this processor wants to access some memory location which is over here, then it has to go through the interconnect network and therefore it is larger. Such architectures are also called as non-uniform memory access architectures because the latency is not uniform. Right? Both centralized shared memory and distributed shared memory support the abstraction of a shared memory architecture. That means that the memory is shared across these different processors and processes, and therefore interaction can happen through this shared memory abstraction. Okay. Now, how do we implement this centralized shared memory? If I take a server motherboard with only one processor socket in it, right? That particular socket may have 4 cores, for example, each core having its own L1 cache and L2 cache, which are private to the core, and maybe a shared L3 cache. But all of these cores will access a common memory, a memory module, which is across a single memory controller, right? So this represents a uniform memory access architecture, right? Because the latency experienced by any core to access the memory is the same, right? Now let's look at another architecture in which my server board has 2 sockets instead of 1 socket, right? In this particular case, each of these sockets will have its own memory controller and an attached memory. Okay, and all of these cores can actually access this memory by just going through the L3 cache and the memory controller and then access the data. But if this core wants to access the data in this memory, then it has to go through this interconnect network, which is the quick path interconnect in this particular case, and then go to the memory controller in the other socket and then access the data from that. Now you can see that the memory access time is non-uniform, and vice versa for this particular socket. This represents what is called a distributed shared memory architecture. For example, if my server motherboard consists of 2 or 4 sockets, each socket having, let's say, 8 cores, then I have, let's say, with a 4 socket system, I have 32 cores, right, of processor cores with a non-uniform memory architectures. In today's context, each processor or each socket itself supports not just one memory controller but multiple memory controllers, right? That also represents a kind of a non-uniformity, so to say. Okay. Now let's talk about the third class of architectures, which are what are called as the distributed memory architectures or the message passing architectures. In the message passing architecture, each processor has its own private cache and memory, which is what we are going to call as the compute node. But then one processor cannot access the memory of another processor, right? So this is essentially the architecture of a cluster computer, right? The interaction between these processors can happen by means of explicit messages, and therefore it is also called the message passing architecture. So it's a cluster computer or message passing architecture or distributed memory architecture. Essentially, this does not support shared memory abstraction. Okay, so such kind of a computer is what you call as the distributed memory architecture or a cluster architecture, in which the processing nodes are connected with each other by means of an interconnect network, and the interaction between the processes can happen by means of explicit messages. Again, you can use your multi-core architectures to implement this kind of a distributed memory architecture. So in this case, what you do is that your quick path interconnect is essentially connected to the IO hub, which in turn is connected to the network interface card by means of the PCIe Express bus. Then this network interface card is connected to a network switch, and multiple such nodes are connected to the network switch to essentially give you an architecture in which there are multiple nodes which are connected to each other by means of this network interconnect switch, right? And then within each node, you essentially have multiple processor cores, or each node by itself is a kind of a distributed shared memory architecture. So this is essentially a hybrid architecture in which you have the nodes which connect to each other by means of distributed memory architecture paradigm, and within each node you have a shared memory paradigm. Okay, that's essentially the architecture that we're talking about. Okay, now I will stop here because there is a question that came about with two sockets. It's probably a good time to take that question.
I think, sir, the answer is, it's been answered by you itself.
Okay.
I was thinking, whether it was connected through bus, for example, two socket, are they connected through a bus? So it's
Yeah, there is
not.
what is called, it again varies from processor to processor. In the case of the Intel, it is called the quick path interconnect.
Okay, so some, let's say, is it also a kind of protocol or some standard thing, or
Some kind of a protocol, yeah.
Okay,
Yeah.
thank you.
Okay, so when the processor is addressing certain memory locations, depending on the memory locations and how they are mapped to different controllers, then it's automatically routed through the quick path interconnects to go to the other controller. Okay, so it's basically the memory address decides, which controller will address that particular request, and then that request is automatically routed to the appropriate memory controller. That's the way to think about it. Okay. All right. Are there any more questions? Because otherwise we could spend the next 15-20 minutes on the cache coherence problem. All right. So let's get on to the cache coherence problem. So once again, let's look at the shared memory architectures and how these shared memory architectures are implemented using the multi-core processors, whether you have the notion of a distributed shared memory or the notion of a centralized shared memory. Here is an example of a centralized shared memory. Here is an example of a distributed shared memory. In both cases, what you see here is that each processor has its own set of private caches, right? These private caches are going to cause some problem, which is what we are going to refer to as the cache coherence problem. And this is going to exist irrespective of whether you have centralized shared memory or distributed shared memory. For example, the L1 and the L2 caches in all of these examples, right, in all of these cores, is one source of a cache coherence problem, right? And particularly when I talk about a centralized shared memory, the L3 cache is not a problem because any data which is there in the L3 is accessible to all the cores, and therefore that by itself does not create any cache coherence problem. But then when I go from this to the distributed shared memory, where I have the L3 cache which is shared by some set of cores on this socket, and the L3 cache which is shared by some set of cores on the other socket, now also creates cache coherence problem. And we will see what this cache coherence problem is next. Okay, so why are we talking about caches, right? Caches.
Sorry to interject, but like, what's a socket?
Oh, a socket is basically a processor which consists of these multiple cores, right? For example, when you buy your desktop system typically consists of a socket. For example, whatever you say, Intel 6238, right, processor, right, that consists of multiple cores. That's essentially one socket, right? Another way to think about it is that when you open up your desktop, you see a motherboard, and in the motherboard there is a CPU and a CPU fan. What you call as the CPU or what you call as the processor is basically what we call as the socket, right?
I see. Thanks.
In server motherboards, you could actually have multiple sockets or multiple processors. Okay, so caches play an important role in multi-core architectures, and they help reduce the average data memory access time. Because if you didn't have caches, then every request has to go to memory, and particularly in the case of a centralized memory, or even in the case of a distributed shared memory, right, you have to go through the interconnect network to access the memory. And if there are no caches, then every request has to go through the interconnect network, which is going to load the interconnect network and going to increase your memory access latency. But at the same time, the moment you start having these private caches, it's going to create a problem, because if you bring in some data into a private cache, and if that processor modifies the data, then that data is modified or updated only in the private cache of processor P1, whereas processor P2 will continue to read the old or stale copy of the data. And this problem is what is referred to as the cache coherence problem. Let's see this example here in the case of a shared memory architecture with, let's say, 3 processors. Okay, let's assume that we are talking about a centralized shared memory. Okay, and there is a single memory module which holds the data. And let's think of 3 processes which are executing on these 3 different processors, which is basically they are having the same shared address space. Okay, now let's talk about a single variable called u, which initially has a value 5. If processor P1 tries to read this variable, then a copy of this memory block would be put in the private cache of P1, and subsequent reads from P1 would read the value of u from the private cache. Similarly, if P3 also wants to read the value of u, it can also cache a copy of this u in its private cache. Right? There are no problems up to now as long as processors only want to read this shared data. But the moment one of these processors, let's say P3, wants to modify the value of u, right, from 5 to 7, if it goes and updates this value in its private cache, assuming that the cache is a write back cache, so the writes are only written into the cache and not into the main memory, right, then P3 will have the value of u as 7. If there is a subsequent read from P1, right, if there is a subsequent read from P1, P1 will happily read the old value from its cache, which is the stale value. And therefore, whatever P1 computes may not necessarily be correct. Right? Similarly, if P2 wants to read the value now, it might try to get the value from memory, which is also stale, and therefore might get the older value. This problem is what is referred to as the cache coherence problem. Right? Okay. If the cache is not a write back cache but a write through cache, maybe P2 when it reads its value may read the value as 7, but still P1 can continue to read the old value of 5, right, as long as the cached block stays in P1's private cache. Right? The fact that each of these caches is private is important because they all have their own copy of this variable, and this copy could become stale when some other processor is updating it in its private cache. Okay. So the idea is not to allow these processors to read the stale value. In order to achieve that, then what has to happen is that when a processor is trying to update a value or modify a value, it has to make sure that the stale values in the other processor's private copies are removed. Right? So such kind of an approach is what is called as the invalidation. So whenever a processor wants to write a shared location, then it has to make sure that any other processor which has a copy of this has to be invalidated. Right? Such an approach is what is called as the invalidation based cache coherence protocol. If the other copies are also updated to the correct value, then it is called an update based cache coherence protocol. I will give you an example of this as we go by. right? And whether it is an invalidation based protocol or an update based protocol, they can be implemented using either a Snoopy cache coherence protocol mechanism or using a directory based cache coherence protocol mechanism, which I will talk about little later on, right? This is essentially a hardware solution for the cache coherence problem. One could also think of a software solution for the cache coherence problem, which is somewhat inefficient, but is cheaper because there is no associated hardware with it. Okay, we are not going to talk about the software cache coherence approaches. We will only focus on this invalidation based hardware cache coherence approach. So again, let's take the same example, and then there in the next slide. Okay, so let's take the same example. When processor P3 wants to write the value of U to 7, right, before it can actually write and modify the shared copy, modify the private copy of P3, it has to send an invalidation message on the bus. And every processor which is actually snooping on the bus sees that in case it has the same cache block which P3 is trying to write, then this invalidation message is going to tell them that they have to invalidate that particular cache block. So when this processor is trying to write U as 7, then every processor will snoop on the bus and then find out that if it has that particular cache block, it will invalidate that cache block. And so will be the memory block. So both the memory and the cache will be invalidated, and they will send some kind of an acknowledgement signal, or maybe there is an implicit acknowledgement that happens, after which processor P3 can go ahead and modify the value of U. If it can be done now in this way, then what happens is that when P3 writes a value of U to be 5, right, it also ensured that no other processor had any stale copies. And it has achieved this by means of invalidating all of the other copies. Right? In the case of an update based protocol, instead of invalidating, you will actually go ahead and update the value to U as 7. That's the only difference. But again, that also happens by means of snooping on the bus. Okay. Later on, we will talk about how this invalidation based protocol is implemented as a finite state machine. And there are different ways of implementing this invalidation based protocols that also we will talk about. Okay. Let me go back to the previous slide where I was trying to say something. Right. Okay. So I was essentially trying to talk about the snooping part and updation versus invalidation, which I have already explained. Okay. Now let's see. So when do we use or when is it beneficial to use invalidation based protocol, and when is it beneficial to use update based protocol? Again, cache coherence is something which is implemented as a part of the processor and the processor caches, right? So it comes with a particular version of the protocol. It either comes with the invalidation based protocol or it comes with the update based protocol. But let's see what are the advantages and disadvantages of these two protocols. If it is an invalidation based protocol, then what happens is that because the other processor's copies are invalidated, when those processors try to read that value again, they are going to incur a cache miss. This is what we are going to call as the coherence miss, right? The miss has happened because of a coherence related invalidation, right? And they will incur the miss penalty for this miss. That is the downside of invalidation based approach. But the positive aspect of the invalidation based approach is that if a processor is trying to write the value again and again on a shared variable, then only on the first time it has to send the invalidation message, and after it has been invalidated, no other processor would have a copy of this data, so it can continue to update this as long as nobody else has a copy of the data. So future writes will not incur many many coherence related traffic on the shared interconnect or on the interconnect network. Again, as we talk about one of these interconnect protocols, you will understand what I mean by this. Okay. As opposed to this, when you talk about an update based protocol, if the data is updated, then a future read will not incur a miss, but it will be a hit, and therefore you could save some cycles because of that. But the downside is that every write, you have to send that traffic across all the to all the processors, and that could be a overhead. Okay, now let's talk about a specific version of an invalidation based protocol, which implements it using a finite state machine having three states, right? These three states are called M, S, and I, and that is why this protocol itself is called as the MSI protocol, where M stands for the modified or dirty modified data, S stands for shared data, and I stands for invalidation data. Okay, so let me just try to explain this without going into these details. Let me just try to explain this by means of the state transition diagram. Let's assume that initially a cache block, right, is in the invalidate state in the processor. That means that that particular processor has not fetched the data. So let's say initially it is in the not valid kind of a state. This data was not brought into the cache. Now, if the processor tries to read this data, okay, then the data is brought from the main memory and put into the private cache of this processor. Because at least one of the processor has the data in its private cache, the data item goes from this invalid state to what is called the shared state. Okay, so whenever there is a read for this data, it goes from the invalid state to the shared state. And at that point in time, there is a bus read signal which is being given, which is what is being snooped by the other processors. Because nobody has a shared copy of this, nothing else is going to happen, right? Once the processor has a copy of this data, it is in the shared state, it can continue to read this data as long as it wants to read this. But if it wants to write into this data or write into one of these words, then it has to generate a processor write signal, and that processor write signal moves this data from the shared state to modified state, because now the cache block has been modified. And when this happens, it sends what is called the bus read exclusive signal. Okay, let's see how this bus read exclusive signal is going to affect the state of other processors and their caches little later. And similarly, when the processor is in the modified state, it can continue to read or write this data as long as it wants, because when it is in the modified state, only this processor has the up-to-date copy of the data and no other processor will have a copy of the data. So it can continue to read it and it can continue to modify without having to worry about informing others. Right? That's the advantage of the invalidation based protocol. Now, when the processor is holding this data in this modified state, right, let's say that, let me take this particular one, right, if at that point in time, let's say some other processor wants to read this data, read this particular block, then that read would actually cause a bus read signal, which is what is going to be snooped by this processor. And because this particular block is in the modified state, then the processor would change the modified state to what is called a shared state, and then this processor and the processor which is requesting this data together will be in the shared state and they will have copies of this data. So that is what is explained by means of this state transition diagram. If the data is in the shared state and if some other processor wants to write into this data, then it is going to generate this bus read exclusive signal. And when you see this bus read exclusive signal, you have to invalidate your copy because somebody else wants to modify this data. So you essentially invalidate it. Okay, a couple of more arcs here. When the processor is in the modified state and when it sees some other processor trying to do an exclusive access to this, which means that they are trying to do a write into it, then it basically invalidates the data, and then it flushes the value to the main memory so that the up-to-date copy is written into the main memory, from where that processor can read that value, right? Similarly, if it is in the invalid state and it wants to write into the data, then it copies the block and it also generates what is called the bus read exclusive signal, so that any other processor which has this data in the shared form can actually go ahead and flush it. Sorry, go ahead and invalidate it, right? So this is how the MSI protocol works. And there are more complex protocols like the MESI protocol or the MOESI protocol and so on. Essentially, all of this, what they are trying to see is that making sure that any particular block can be in a shared state where it can be shared by multiple processors. But if one of the processors wants to modify the data, then only one of them has the copy, and all other processors, right, if at all they had a copy, they will invalidate them and they will no longer have a valid copy of the data. That's essentially what has to be preserved by the MSI protocol, but by any cache coherence protocol, not just the MSI protocol. Okay. So I'm not going to go into the details of other cache coherence protocols. So for example, let me just say that there is something called an MESI protocol, which is complex, right, and so on. But let me just conclude our discussions by making one note, which is about the scalability of the Snoopy protocol. So in order for us to implement the Snoopy protocol, you need to have some kind of a shared interconnect, such as the shared bus, so that the other processors can be snooping on the bus. But a shared bus is a kind of a bottleneck beyond for a large number of processors. For example, if you want to support something like 16 cores or 32 cores, then implementing them on a shared bus would actually affect its performance. So the moment you go to a non-shared kind of an interconnect network, then implementing Snoopy protocol becomes difficult. So instead of implementing Snoopy protocol, then what you have to do is that if there is an invalidation that has to be sent, then that invalidation has to be sent in the form of a broadcast message to all the processors, right? But that broadcast message is going to be expensive, because for every invalidation, if I have to send a message to all the other 32 processors or 32 cores, that's going to be a very ineffective way of doing it, right? So how does one implement these invalidation based protocols if I do not have a shared bus interconnect, because Snoopy protocol is no longer very useful? So for that purpose, people have proposed what is called a directory based protocol. And the idea of the directory based protocol is that explicitly the memory or the cache controller maintains information of which other processor has a copy of this memory block. And therefore, if a processor wants to write the data, then it can actually send explicit invalidation messages only to those processors which have a copy of the data, right? So you essentially maintain what is called the directory information, which specifies for each cache block, right, which other processor has a copy of it, or for each memory block, which other processor has a copy of it. So if you want to invalidate a particular memory block or a cache block, then by looking into the directory, the processor can send specific invalidation messages to those processors which will have a copy of the data. But otherwise, the MSI protocol or the MESI protocol works the same way. It is only that instead of the processor snooping on the bus and getting that information, there are these explicit or direct messages, controller, whatever may be the case, and the processors react to those specific messages. That's how the directory-based protocols work. Okay, we don't have time to go into all the details, but then in systems which have a large number of processor cores, more than 8 cores, typically it is a directory-based implementation. That's what people talk about. Okay, so with that, we will possibly conclude our discussions on cache coherence. As I mentioned, the directory essentially stores who are the sharers, right? and whether and when you have multiple sharers, obviously it is not in the dirty state or in the modified state, it is in the shared state. But if it is not in the shared state, if it is in the dirty state, then it also tells you which processor has the modified data value as a part of the directory information. Okay, so that kind of concludes our discussions on cache coherence. There is one related problem that we have to talk about, which we haven't talked in great detail, which is what is called the memory consistency. So let me very briefly tell you how this relates to the cache coherence protocol. When we talked about stale copies and having to invalidate these stale copies, we were kind of going with this intuitive understanding that all future requests should not be reading the old copy, right? This essentially is in some form formalized by the underlying memory consistency model, right? Because when you say that somebody should not be reading the stale copy, what exactly is meant by a stale copy? We're just going by this intuitive understanding. When a particular processor modifies, then from in all future occurrences, no other processor should be reading the old value. That's what we meant. But we try to formalize this notion by means of what is called a memory consistency model, which Professor Madhu Mutyam will talk about in one of his future lectures. Okay, so with that, we will conclude our discussions. If you have any questions, I would be happy to answer them.
So,
yeah.
So in the state diagram for the MSI protocol, we started from the invalid state. So why we started from the invalid state there?
Why we stopped or started?
Started, like
it doesn't matter.
Like initial conditions like that. That's basically my question.
So the initial condition is that the processor has not copied the data, correct? Has not brought the data from memory to the processor. That's the initial condition, right?
Okay, so
that is why we started. Yeah, that's why we started from the invalid state. As soon as it reads it, it goes into what is called the shared state, right? Okay. So the first read will bring the memory block into the cache, and that will make it as shared.
Okay, and what exactly is the meaning of flush here? Like we are basically
so this flush you are talking about, correct?
Yeah, this like
this one more over here. Okay, so where is this flush happening from? From the modified state, right? And what is a modified state? What does it mean really?
That it has the the latest copy of that particular.
The latest copy, right? And only it has the latest copy. Nobody else has the latest copy, not even the memory. So what does flush here means? When I evict this or when I go from the modified to invalid state, I have to write back the value into the memory, right? The modified value has to be given to the memory, is flushed to the memory, right?
So why it's coming to the invalid?
So let me again tell you, right? So this is the case when, let's say, P3 has written U is equal to 7, correct? Now at this point in time, P3 sees that there is a bus read X signal, right? When P3 sees a bus read X signal, it means that some other processor, maybe P2 or P4 or P7, wants to modify U, correct? That is when the bus read X signal will come, right? And when the bus read X signal comes, right, it has the modified copy of U is equal to 7, right? So it has to write that value back into the memory, right? So that is what is the flush part of it. Whereas in this particular case, it only sees a bus read signal as opposed to a bus read X signal. A bus read essentially means some other processor wants to read this data. So I don't have to invalidate my copy. I can continue to keep my copy, but I can't be in the modified state because now two of us are sharing the data. So I go from the modified state to the shared state where both P3 and P2 are sharing the data. and both have the same common understanding that u is 7, and the value of u is equal to 7 is also written into the memory because now the data is in the shared form. Okay, so here flush means that the modified copy which was exclusively residing on this processor's private cache is now being written into the memory, right? That is what is a flush about. Whether it goes from the M state to S state or M state to I state depends on whether the other processor's request is just for a read or for a write. Okay.
All right. And like suppose like if it sees both the signals, like there are multiple such processors. So like if such one processor wants to read and another processor wants to write the data. So in that case,
Okay. So something needs to happen, right? We are talking about a bus, right? If it is a Snoopy protocol, we are talking about a bus. Correct?
Yes, sir.
So in a bus, what happens? I told you, at any given time, there can be only one request. So there is going to be ordered in some way.
All right.
Right? So that takes care of things. But if it is not a bus, right, if it is some other interconnect network, right, then this ordering may happen in any way, like what you have suggested. Then, of course, you need some extra mechanisms to ensure how to take care of these things, right? And that depends on, right, how exactly the request comes to this processor P3, right? And somebody else might be ordering the event somewhere over there. Okay?
Yes, sir.
Any other questions?
So I have a question from previous lecture. So can I ask it now? Or like,
Sure. Go ahead.
So we talked about the virtual to physical mapping, like when we have to like bring, like if there is a cache miss, we have to do some address translation. But in some cases, we also might want to do the physical to virtual mapping, like when we are bringing the data from main memory to our L1 cache. So how does like?
Well, first of all, let me just make this very clear, right? So to access the data, you have to do the address translation from virtual address to physical address. Right? Not because you had a cache miss, you have to do a address translation. Okay. Address translation is essential as long as, address translation has to be done as long as you don't have a virtually indexed, virtually tagged cache. In all other cases, you have to do an address translation. Okay, whether the data is available, is a hit in the cache or is a miss in the cache. Only in the case of a virtually indexed, virtually tagged cache, right? You can first access your virtual cache, and if the data is already available in the virtual cache, because you are only using the virtual index and virtual tag, you don't need to do any address translation further. If it is a hit, you are done. Only if it is a miss, in the case of a virtual cache, you talk about doing an address translation. Correct? So understand this properly. If you have a physical cache or if you have a physically indexed, virtually tagged cache, as long as some parts of the address is physical, right, you need to do the address translation irrespective of whether it's a hit or a miss. Okay, even to find out whether it's a hit or a miss, you need to do the address translation. Okay. Now, what is your question?
So my question was like, suppose we have a virtually indexed, virtually tagged cache.
Virtually indexed, physically tagged. Correct?
No, virtually indexed, virtually
tagged. Okay.
Yeah.
Sure.
So in this case, like we do not have to do initial address translation.
Correct. You do not have to do initial address translation. Only if there is a cache miss, you have to do an address translation.
So yeah, so we did this. We did the address translation.
Right.
We now wanted to bring back the copy from the requested data from the main.
Very good.
This
very
cache.
good. Yeah.
So now we again have to do this address translation from physical to virtual address.
Okay.
So typically, like how does that happen? Like, is it using the
good?
same?
Very good question. Very good question. This is one complication of a virtually indexed, virtually tagged cache. Okay. As far as I could recall and I know, you don't do the translation from physical to virtual. That you don't do that. The inverse translation you don't do. You instead save the virtual address somewhere so that when the data comes back from the main memory, you use that virtual address to directly store it in the appropriate set. Okay.
Oh, okay.
Right. So you always do translation from virtual to physical. But if you wanted the virtual, then you have to save it somewhere and then use it. Okay. It's a very, very good question. You have thought through this and then you said, okay, now what would happen? But the trick is to save the virtual address when you, so again, you can think of the MSHRs, right? The MSHR is going to hold the information, right? It can hold the virtual address as well as the physical address. So that when the response comes, it sends the physical address to get the response. And then when the response comes, it can use the virtual address to write in the appropriate location in the cache. Correct? So you could use MSHRs for that, for example.
Okay, sir.
Yeah. Thank you. Bye.